The Angel of Independence appears to stand exactly where Mexico City placed it in 1910. But look at the base. 14 steps have been added since the monument was built. Not to make it taller, but because the avenue around it kept moving downward. The monument began to look as though it were slowly rising out of the street. Then from October 2025 to January 2026, a new satellite operated by NASA and the Indian Space Research Organization measured parts of Mexico City sinking by more than 2 centimeters in a single month. If that pace continued for a year, the ground would fall almost 10 inches. The city is not sliding into the sea. It sits more than 2,000 meters above it. What is happening is stranger. Mexico City is compressing the Earth beneath its own weight, and a spacecraft can now watch it happen from orbit. This is not a computer prediction of a distant disaster. It is a measurement of movement that has already taken place. Nor is the whole metropolis descending like one enormous elevator. Some neighborhoods move slowly. Others sink many times faster. A building on firm volcanic ground can remain relatively stable while streets on old lake clay drop around it. That difference is what tears pipes, tilts structures, changes the slope of railway tracks, and turns an invisible geological process into cracks people can see from their windows. The satellite did not discover that Mexico City sinks. Engineers documented the problem a century ago. What the new image provides is a sharper citywide view of where the damage is accelerating. Now the spacecraft is called NISAR, short for NASA-ISRO Synthetic Aperture Radar. Unlike an ordinary camera, it does not need daylight, clear skies, or a beautiful view. It sends microwave signals toward the ground and records the echoes that return when the satellite passes over the same place. Again, tiny changes in the timing and phase of those echoes reveal whether the surface has moved toward or away from it. By combining repeated observations, scientists can detect motion too small for the human eye to notice. On the new map, the fastest sinking areas appear in deep blue. The colors are artificial, but the movement is real. A city that looks solid from the street becomes a field of different velocities from space. To understand why, we have to remove nearly every road, tower, stadium, and neighborhood from the map. Long before Mexico City existed, this was the Basin of Mexico, a high-altitude bowl enclosed by mountains and volcanoes. Water flowed down from the slopes, but had no easy natural route to the sea. It collected in a chain of shallow lakes. The largest was Lake Texcoco, and its floor accumulated extremely fine sediments over thousands of years. Those sediments held enormous amounts of water inside microscopic pores. They could support reeds, wetlands, and an aquatic civilization. They were never designed to support the weight and water demand of one of the largest urban regions on Earth. The Mexica understood the basin as a landscape of water. In the 14th century, they founded Tenochtitlan on an island in Lake Texcoco and connected it to the shore with causeways. Canals carried people and goods through the city. Aqueducts delivered fresh water. Dikes helped separate fresher water from the saltier parts of the lake system, and chinampas created extraordinarily productive growing areas in the shallow wetlands. Tenochtitlan was not safe from flooding, and its water system required constant labor. But its basic logic was adaptation. The city did not pretend the lake was absent. It organized life around the fact that water controlled the basin. After the Spanish conquest, that logic changed. Colonial authorities rebuilt the capital over the defeated island city, favoring streets, plazas, wheeled transport, and buildings that belonged on dry ground. Seasonal flooding became an enemy to be expelled. Across the following centuries, an immense sequence of canals, cuts, tunnels, pumps, and drainage works carried water out of the closed basin. Lake Texcoco retreated, wetlands were filled. The modern city spread across land that earlier generations would have recognized as lake. It was one of history's most ambitious attempts to turn a water landscape into a dry one. The transformation solved one problem and quietly created another. Removing the lake did not remove the clay beneath it. Mexico City gained a surface on which it could build, but that surface behaved less like bedrock than a thick archive of mud and water. As the population grew during the 20th century, rivers and springs were no longer enough. The city increasingly pumped groundwater from the aquifer below. Wells reached beneath neighborhoods, factories, and fields. Water that had taken years, centuries, or longer to enter the basin was pulled upward to serve homes and industry. The visible lake disappeared, while the invisible water below became essential. An aquifer is not simply an underground lake with a roof over it. Water occupies pores and fractures between grains of sand, gravel, silt, and clay. That water helps carry part of the pressure imposed by everything above. When pumping lowers the underground pressure, more of the weight transfers to the mineral structure. The soft lake sediments begin to press together. Water is squeezed from the clay, pore space collapses, and the land surface drops. Imagine a stack of wet, porous pages being compressed under a growing city. Once many of those spaces close, the pages do not spring back to their original thickness. The lost ground is largely permanent, and the aquifer may lose some of its ability to store water in the future. This is why rain alone cannot lift Mexico City back into place. A wet season can slow or alter short-term movement in some areas, and carefully managed recharge can protect groundwater. But water cannot simply reopen every microscopic space crushed over decades. A major scientific study combining more than a century of leveling records with satellite and GPS observations found that subsidence in the hardest hit zones has remained remarkably persistent. Different studies, periods, and neighborhoods produce different rates, but researchers have measured hotspots from roughly 35 to 50 centimeters per year. The new NISAR result of more than 2 centimeters per m/onth is a recent snapshot, not the first chapter of the story. Over the past century, extensive parts of the urban area have descended by roughly 10 to 14 meters. That is not the height of a curb. It is the height of a 4-story building removed from beneath the city. Yet the change is easy to miss, because people, roads, and low buildings can all move downward together. There is no single morning when residents wake up and find the skyline suddenly lower. The evidence accumulates in repairs, a new step at a monument, a pipe that no longer meets its connection, a doorway that will not close, a wall separated from the house beside it, or a street that has become a shallow bowl. The Angel of Independence is one of the clearest demonstrations because its deep foundation and the surrounding ground have not moved in the same way. As the avenue subsided, the monument appeared to rise, and new steps had to bridge the difference. Historic structures elsewhere have required elaborate stabilization as their foundations settled unevenly. But the most dangerous damage is often less photogenic. A city can tolerate a broad area sinking at a similar rate more easily than it can tolerate 2 adjacent blocks moving differently. Engineers call this differential subsidence. It bends the city rather than merely lowering it. The pattern follows the buried geography. Western districts built closer to volcanic rock generally behave differently from eastern and southeastern areas resting on thicker lake deposits. In places such as Iztapalapa, Tlalpujahua, Xochimilco, and the wider metropolitan zone toward Valle de Chalco, sharp changes can occur over short distances. One side of a structure may descend faster than the other. A road crosses from firmer material onto compressible clay. A water main runs through several geological zones without changing its design from orbit. The color boundary may look elegant on the ground. It becomes a fracture. Water pipes are especially vulnerable. Buried networks were built with an expected slope, depth, and alignment. When the soil moves unevenly, joints separate and pipes crack. Treated water leaks into the ground before reaching a tap. Residents then need more water from wells or tankers, even as additional pumping contributes to further compaction. The city falls into a brutal feedback loop. Groundwater extraction helps the land sink. Sinking damages the system that carries water. Damaged infrastructure loses water, and scarcity increases pressure to extract more. Mexico City is not only sinking because it is thirsty. In some places, it is becoming thirstier because it is sinking. Drainage faces the opposite problem, but the same moving ground for centuries. Engineers tried to give water a downhill path out of the basin. Subsidence changes that slope. Parts of the city have fallen relative to older canals and outlets, forcing pumps to do work that gravity once performed. New deep tunnels and pumping stations can move extraordinary quantities of stormwater and sewage, but they must serve a surface that continues to deform above them. When intense rain arrives, paved ground sheds water rapidly, low areas collect it, and drainage capacity can be overwhelmed. The old lake has been erased from the street map, yet water still searches for the low points it once occupied. This produces Mexico City's most painful paradox. A metropolis built over lakes can flood during a storm, while households in the same urban region wait for reliable drinking water. Flooding does not mean the aquifer has been restored. Much of the rain runs across concrete, mixes with waste, or is pumped away before it can infiltrate safely. The soil beneath the city may contain water, but extracting it quickly enough for millions of people lowers pressure in the layers that support the ground. Too much water can be present at the surface at the wrong moment, while too little usable water is available in the right place. Transport systems must also live with this motion. Roads are repeatedly resurfaced, but a smooth layer of asphalt cannot stop the soil below from changing shape. Bridges, sewers, airport facilities, and rail lines depend on precise levels and connections. Research into the Mexico City metro has shown how differential subsidence can alter track geometry and place additional stress on infrastructure, especially where routes cross contrasting ground conditions. Subsidence should not be used as a simple explanation for every accident in the city. Its real danger is more patient. It changes the assumptions under which infrastructure was designed, then forces engineers to inspect, adjust, and rebuild while the movement continues. Earthquakes add another layer of fear, but they are not the same process. Mexico City is far from the Pacific coast where many powerful earthquakes begin, yet the soft sediments of the old lakebed can amplify and prolong shaking. That is why distant earthquakes can feel so destructive in the basin. Subsidence, by contrast, is mostly the slow compaction associated with groundwater pressure and the weight above. The two problems share the same vulnerable geology and can interact in the stresses they place on structures. But the city is not sinking because earthquakes are pulling it downward. Keeping the distinction clear makes the risk more understandable, not less serious. For residents, there is rarely a dramatic line between geology and ordinary life. It may begin as a diagonal crack across a bedroom wall. A floor develops a slope. Rain enters through a gap, a sewer backs up, a family is told that repairing the plaster will not solve the moving foundation. Wealthier property owners may pay for engineering work or relocation. Lower-income households are more likely to live with repeated damage, unreliable water, and streets where public repairs lag behind the ground. The satellite measures centimeters without knowing who can afford them. The social consequences are not nearly so equal. The latest space map therefore matters for more than producing a shocking image. Ground instruments provide highly accurate measurements at specific locations, while radar can reveal the pattern across a vast metropolitan area. NISAR is designed to revisit land repeatedly, allowing scientists and authorities to track how movement changes through seasons and years. That information can help identify dangerous gradients, prioritize inspections, protect pipelines, and decide where construction requires different foundations. A satellite cannot repair a street, but it can show that two streets that look identical are standing on very different futures. Can the sinking be stopped? There is no switch that can be turned off without consequences. Millions of people need water every day, and suddenly closing wells would create a humanitarian crisis long before it rescued the ground. Even if pumping were reduced, thick clay layers can continue draining and compacting for years. Research suggests that parts of the basin may remain vulnerable for many decades because the process has built up over generations, and the meters already lost will not return. The realistic goal is not to make Mexico City rise. It is to slow additional damage, manage the differences between sinking zones, and stop treating the aquifer as if it were bottomless. That requires several solutions at once. Leaking distribution pipes must be repaired, so water already captured is not wasted. Treated wastewater can be reused for purposes that do not require drinking quality. Stormwater can be captured and cleaned rather than expelled as quickly as possible. Carefully chosen recharge projects can help more water enter the aquifer without contaminating it. Wetlands and open ground can preserve places where the basin still absorbs rain. Water imported from outside the valley can reduce local pumping, although those systems are expensive, energy-intensive, and vulnerable to drought elsewhere. None of these measures is a miracle together. They can buy the city something it has repeatedly tried to engineer away. Time the hardest solution may be cultural rather than mechanical. For 5 centuries, power in the basin was demonstrated by controlling water, draining it, channeling it, hiding it underground, and building as though the lake were gone. But Mexico City's geology continues to reject that fiction. The basin is not an empty platform beneath the capital. It is an active part of the city, storing water, transmitting pressure, amplifying motion, and remembering every layer of the vanished lake. That is why the NASA map feels so unsettling from hundreds of kilometers above Earth. A radar instrument can see a history that street level conceals. The deepest blue areas are not simply geological anomalies. They trace the ancient lakebed, the growth of the metropolis, the placement of wells, and the unequal burden placed on different neighborhoods. Modern Mexico City and ancient Texcoco occupy the same space. One is visible in roads and towers, the other is visible in movement. The city is not about to disappear into a giant hole, and alarmist images of a sudden collapse misunderstand the danger. Mexico City will remain one of the world's great capitals. The challenge is that it must continuously rebuild itself on ground whose elevation is changing block by block. Every new pipeline, rail extension, airport connection, home and drainage project enters a race against that motion. Ignoring the sinking makes each investment more fragile. Measuring it turns an invisible threat into something engineers can plan around. There is a lesson in the contrast between Tenochtitlan and the metropolis above it. The older city survived by making water part of its design. The modern city became enormous by trying to push water out, then drawing more of it from below. Returning to the past is impossible. More than 20 million people cannot live as an island city of the 15th century. But the principle remains useful. A city in this basin cannot defeat water permanently. It can only decide whether to fight the landscape at increasing cost or learn, once again, to build with it. 14 added steps at one monument, more than 2 centimeters of movement in a month in some zones, up to 4 stories of elevation already lost across a century in extensive parts of the urban area. Each number describes the same transformation at a different scale. From the pavement, it appears as a crack. From a lifetime, it appears as a monument rising out of its avenue. From space, it appears as an entire city moving in different directions at once. NASA can see Mexico City sinking because the ground is telling the same story the vanished lake has been telling for 500 years. The water may be hidden, but it never stops shaping the city.